So welcome to this first workshop for ACS 2021. I think the meeting is going to be really exciting. There's a lot of content that we would like to get through, and a lot of interaction that we would like to have. And so obviously we start the program with a couple of workshops, and the workshops are designed to be interactive. This workshop particularly is designed to be interactive, not just for the 2 hours that we spend here today, but going forward, and hoping that we can create a network of like-minded innovators in cytometry that are interested in pushing the boundaries. You know, there's a lot of boundaries to push now. Cytometry used to be a relatively stepwise at incremental gains, you might say, in terms of, you know, adding lasers and adding detectors and things like that. But I think in the last couple of years, what we've seen is a real fresh look at this, and we see technologies like microfluidics and genomics and label-free imaging, all these kind of things that are coming to the fore that are really adding to the power of cytometry. And so, you know, those of you who know me, we've been talking about this for years and saying cytometry is not just flow cytometry. It's much broader than that. And that's what we wanted to try to do today, is to show you what, you know, the innovators around the world are thinking about in terms of cytometry, get and hear from you in terms of what you are thinking cytometry is and how it can be advanced. So, quick workshop outline is that we're going to do this introduction. I'm not going to talk for very long. We have such a fantastic lineup of speakers for you today. Some of them can be here, and some of them have provided pre-recorded videos for us, short pre-recorded videos. These are designed to be a snippet of what they are thinking in terms of the cytometry space, and a little bit of a handle for you to be able to reach out to them and to continue that conversation. So don't expect to have full knowledge of what they're doing. It really is just that snippet and that handle for you to start a conversation. We'll start with 4 of those, and then we'll jump into some live presentations, some longer live presentations of 15 minutes each, or 12 minutes plus a couple of minutes of question time with Arnold, Jew, and Stephen. Fantastic speakers. These are local speakers. Really excited to have them here. And then we'll just go back into a few more short talks, and we'll wrap up with a panel discussion of the innovators around here. Before we do that, we are presenting from Sydney, Australia. So, you know, obviously we like to acknowledge the traditional owners of the people, the traditional owners of the Gadigal people of the Eora Nation. They have been here for tens of thousands of years. And so we pay our respects to them, both past, present, and emerging. This is an interactive session, so please do use these links. Open up Slido. Slido is the primary form of communication that we'll be using today. And you can use that QR code to open up the Slido app. And you can, there's 2 parts of that today. There's a couple of poll questions, and there's a Q&A. So the polls will be made live as this, at the relevant point when this talk progresses. The Q&A is a little bit different here today. So please do put your questions into the Q&A of Slido. The reason for that is that because we have pre-recorded speakers, we want to be able to take those questions, pass them on to the speakers, and then pass those answers back to you. As I said at the start, this is the beginning of a conversation. And so just because they're not here, it doesn't mean that you won't get your question answered. And of course, you know, in these circumstances that we all find ourselves in, the remote version of work is one that is going to last. And it's, you know, innovators come from all across the world in all different walks of life. So that electronic form of communications is going to be important until we can hopefully come together and actually have, you know, interactions. And we are thinking about ways to build those interactions, and, you know, whether they're small regional meetings of innovators and things like that. We haven't settled on that, but we're really interested to hear your feedback on that one as well. So if you have any any sort of advice for us or any thoughts about that, just dump them into the Slido too, because that will all be collated. All right, so hopefully you've got your Slido app all up and working, and we'll jump into a few questions. So the first thing that I wanted to do, this looks like it's live, so please do put a vote on this. So the question is, do you consider yourself a cytometrist in inverted commas? So we have some saying yes, I'm not sure. There's 5 responses. This is positive. Yep. There's a couple that say no. This is fully expected. And we do hope that we have captured people in this innovation session that are thinking, I want to interface with cytometry, but I'm not 100% sure if I'm a cytometrist. So, and hopefully what we'll see as we go through is that you probably are a cytometrist, but it's just not a traditional one. And so we're really excited to try to bring those non-traditional cytometrists into the fold and make cytometry a much better space. So there's a couple of responses here. There's a few more that we're probably still missing. It's starting to even out, but we might, we're 50-50 now. So that's not a bad mix, I'd say. All right. Well, excellent. Okay. So I'm going to move on to the next question, just in the interest of time, but maybe have a think about this question as we go through, because we will ask it again at the end to see whether after we've described what we think cytometry is, whether you still think you're a cytometrist, or whether you think, you are a cytometrist now. So that will be interesting. So perhaps we can do the next question, which is a word association of cytometry. What words do you associate with cytometry? So if we asked this 4 or 5 years ago, I'm highly confident that the things would have been fluorochromes, cell sorting, analysis, those kind of things. So really interested to see what people come up with here. Cell washing, imaging, yep. Cell sorting, fluorescence, yes, they're the common ones. Yeah, absolutely. I mean, if you break down cytometry, it really is just a form of measuring cells. That's certainly, the origins, yep. Facts, multidimensional, yes, absolutely. We are certainly moving into a space where the dimensions are becoming almost limitless. And I recall talking to one of my colleagues and, them talking about imaging cytometry and saying, actually, the number of dimensions in the image is almost infinite. So, as traditional discrete marker cytometrists, we say we've done a good job when we hit 16, 18, 20 colors, but certainly that's not what's happening moving forward. I know David, one of the co-hosts here, has been experimenting with, is it 100+ AbSeq panels, so, and those things are actually getting potentially, I was going to say simpler, but I may refrain from actually saying that, but there's certainly getting more common. That's excellent. So this is really starting to look good. I should say that what happens in these word clouds is that if there is a repeat answer, it tends to get bigger. And so I'm glad to see that there is quite a lot of variation amongst the group in terms of what we're actually thinking about here. So that's really good. All right, I'll give you a couple of seconds to finish off your thoughts on that, and then we'll move to the next poll. Cell measurement. Okay, so we've hit a common thread. So that's excellent. All right, I'm just going to move the slides now, and then we're going to ask what kinds of technologies and innovations fall under the banner of cytometry. So, is this about PMTs? Is it about, lasers? Is it about high-speed imaging? So we'll let you think about this as well. And so I would expect that the responses that we get here are probably slightly different if we asked, you know, the Purdue list versus a group of people that have identified and have identified interest in the innovation space. So. Yep, so we're still talking about imaging and lasers. Microfluidics, absolutely. I haven't seen the term genomics pop up yet, but I suspect that might be because David's not typing. So excellent. So I'm very glad to see that microfluidics has come up rather large. I think that's important. And of course the lasers and the imaging and putting this all together. We do have a single cell genomics. There we go. It's finally come up. So excellent. All right. We'll give you 10 seconds to finish that and then we'll just jump into the talks. But think about these 3 questions as we go forward, because what we're going to do is ask the exact same questions at the end and see how you now see how these change. So, all right. As I said, I'm not going to talk very long. What I wanted to do was to encourage you to rethink how we integrate all of these modalities. And so I use these slides a lot. There's 2 slides here. And what is traditionally has happened is that all of the fields that go into cytometry have set up as discrete modalities. And so the crosstalk between these has been somewhat limited. And I think driving innovation really requires us to take all of these pieces and to put them together into a machinery that allows everything to turn everything else. And when we are able to do this, we get the power of what cytometry is about. So, you know, all of those key terms and things that we were looking at, microfluidics, single cell genomics, lasers, you know, multiplexing, all of those kind of things. If we're talking about biology, we want to stitch those all together so that we can answer fundamental questions in biology or other areas of science that you're working in. I'm, you know, a biologist, but I know that cytometry is not just restricted to biology. So that's one thing to remember as well. The last thing I wanted to do before handing over to David is to encourage you to think about how important cytometry is in the scheme of things. This is a very, very simple diagram taken from the nature methods of the year. And we basically just took all of the nature methods of the year and put them into this timeline and said, which ones do we think are cytometry or cytometry related? And you can see very clearly there that the majority of those nature methods of the year since the inception are related to cytometry and provide cytometric tools. And so if you're joining us for the rest of the conference, please do come by the innovation session because Rita Strack and Rongfan will be talking about some of these kind of technologies in greater depth and how single cell is really, really critical methodology. So with that, what I'll do is hand over to David Galigo-Ortega, who is one of the co-chairs, and he'll take us through introducing the next 6 speakers. Sorry. Thanks, David.
Well, thank you, Rob. And I'm very happy to be here today on a Sunday, a rainy Sunday here in Sydney, and looking at all these many people, innovators, interested in innovators and cytometry. So it's great to be here today. Well, I would like to introduce our first invited talk for the session is Dr. Melanie Jimenez. Melanie is currently a Royal Academy and Engineering Research Fellow and Chancellor's Fellow at the University of Strathclyde, if I pronounce it correctly, in Scotland. And she focuses on new approaches to better characterize biological systems using label-free imaging techniques. She's coming today with a very provocative title, very interesting. What a way to start this innovators session. A dolphin, a bubble, and a cell walk into a bar. Let's see what happens now.
Hi everyone, I am Melanie. I am a Royal Academy of Engineering Research Fellow at the University of Strathclyde. And today we're going to talk a little bit about dolphins. So you might wonder, but what's the link between dolphins and innovation in cytometry? So let's just have a look at the etymology of the word cytometry. So in cytometry, you have that notion of kytos, which means kind of hollow vessels. And cytometry seems to be how we are applying measurements to those hollow vessels. And that definition has been widely used for biological systems, so cells and tissues. But I would argue that you could also apply it to other systems, for example, bubbles. So I think we can agree that bubbles can be seen as hollow vessels. And so a couple of years ago, we tried to apply cytometry principles to bubble or bubblemetry, if you wish. And so this is what it kind of looks like. So similarly to work with cells, we are interested in specific markers. In that particular video, we're interested in the shadow that you can see in the wake of the bubble and how it behaves. And so in order to do cytometry here, we are using high-speed imaging. And I hope that you can see from this video that the high-speed imaging gives you a lot of information on the dynamic on how that shadow is behaving, but also importantly, how it correlates with how the bubble moves and deforms. And that's something that we can call deformability cytometry. And deformability cytometry is something that is particularly interesting to apply when you work with bubbles, because depending on how they are going to deform, they can create quite amazing things. For example, here, you are going to see the birth of a bubble. And this bubble has a very specific shape. That is a donut shape. And this is where our friend the dolphin comes in, because dolphins are really, really good at making those bubbles, those kind of donut-shaped bubbles that we call toroidal bubbles. And so we thought that it would be actually quite interesting to recreate that process in the lab, and also because they have some very interesting properties. So I hope that so far I have been able to convince you that by looking at systems just using high-speed imaging and bright field images, you can actually get quite a lot of information. And you can actually apply deformability cytometry also to cells. So this is what it would look like. So you would typically use a microfluidic system, so a really tiny network of channels to really manipulate with high precision your biological cells. So here, the cells are the black moving dots. And you can really design your system so that you are going to create a deformation that you can image using high-speed imaging. So this is what it would look like. You can see how a cell that initially has a round shape then gets deformed, and you can get those information at really high throughput to analyze a lot of cells per second just using that. And what's quite interesting is that although the field of deformability cytometry is still relatively new, we are starting to see lots of relevance for applications spanning a wide range of disciplines. For example, medical applications, where that deformation brings you something that you wouldn't be able to detect otherwise using other standard cytometry approaches. And so in our case, we've been particularly interested in using deformability cytometry to study time changes in cells. So for example, here you can see how the deformation and the size of a population of stem cells is changing through differentiation. But you also see lots of temporal changes for cancer cells during cancer progression, or immune cells during infection, and many others. So it's a really exciting field. And one thing that we are particularly interested in is also how do you correlate that physical phenotype, so looking at the deformability and the morphology of the cells, to, for example, functions and other phenotyping approaches. So we are looking at techniques on how you can actually isolate cells with specific properties to do then those assays, and really bring the two together to have a more holistic approach on how we characterize cells. So that's in a nutshell what I wanted to present. So the world of deformability cytometry applied to bubbles and also biological systems. So if you are interested in learning more, please do not hesitate to get in touch. You have my contact details here. So yeah, thank you very much. Bye.
Well, that was fantastic. Really, really interesting stuff coming from Dr. Melanie Jimenez. Now we have the second speaker of this session is Dr. Gung Lin. He is a research fellow at the University of Technology, Sydney. And his research activity bridges fundamental and applied aspects of functional micro and nanomaterials, and, if I'm saying it correctly, microelectromechanical system, or also known as MEMS, for bioanalytical and biomedical fields. Over to you, Gungun.
Over the past century, we have seen the great power of MEMS technologies. MEMS has transformed IT industry. Nowadays, we have been able to use handheld smartphone devices, and performance is even better than those earlier computers. Similarly, we expect that MEMS could play an important role in the development of flow cytometry. We hope that in the near future, portable and more affordable cytometers could go out of the labs and go into the field. So we are leveraging the recent advances in magnetic MEMS to develop the next generation of portable cytometers. A very good example of magnetic MEMS is the computer hard disk drive. So if you open the hard disk drive, you may find a sensor called giant magnetoresistance sensor. So it's highly sensitive and it's characterized with a large change of sensor resistance with a small change of magnetic fields. Two elements for magnetic cytometer. Firstly, the magnetic sensor, such as the GMR sensor or Hall sensor, can be used as the detectors, replacing the optical ones. Secondly, magnetic particles are used as labels of cells or carriers of biomolecules and replacing the conventional fluorophores. In typical flow cytometry assays, cells labeled by magnetic nanoparticles are passed across a sensor one by one, so that the stray magnetic fields from the particles could be detected by the sensor. This eventually translates into time-of-flight electrical signal. The electrical signal carries abundant information regarding cell size and other information such as the abundance of surface molecules on the cells. A couple of magnetic flow cytometers have been demonstrated, including rows based on Hall sensors or GMR sensors. Sheath focusing is the primary approach to divert cells to the sensors for detection. So both systems demonstrated high accuracy in detecting circulating tumor cells in blood samples with accuracy up to 90%. Certain degree of multiplexing can be achieved with the ability to simultaneously analyze up to 3 biomarkers on single cells. And the theoretical threshold throughput can be estimated based on the sampling rate as well as the number of samples per detection events, and that gives about 10 to the power of 6 to 10 to the power of 7 cells per minute. Well, in addition to cell-based analysis, we further extended the application of magnetic cytometry to multiplexed biomolecular analysis. And this is also one of the major applications of conventional optical flow cytometers. The relevant technology is so-called suspension array technology, and that has been typically based on fluorescently barcoded microparticles as the molecular carriers. So for magnetic flow cytometry, we are developing magnetically encoded microparticles, and the particles can be differentiated by their unique magnetic stray field patterns. So eventually, we could use GMR sensors as those used already in the computer hard disk drive to read out these patterns. So there are a couple of benefits of using directly magnetic beads for multiplex biomolecular analysis. And firstly, they could streamline the assays. and they can also integrate the isolation, attenuation, as well as the detection process in a single system. Well, let us do a few aspects that require further development. Current cell-based barcoding assays can achieve the same level of multiplicity as the optical approaches. We have been able to engineer the magnetic core at a microscale, and this cannot be easily done at a nanoscale. Sensitive detection relies on focusing the particles to the proximity of the sensors, and this may ultimately affect the throughput. In the future, dedicated electronic designs are needed in order to make the whole device really compact.
All right. That was great. Very interesting to see this magnetic cytometry. Our next innovator talk, also as a recorded talk, is coming from Dr. Jingjing Zhao. Jingjing is currently a postdoctoral scholar at Stanford University School of Medicine in the USA. And his research interests include optical coherence tomography, instrumentation, microfluidic flow cytometry, and diffractive optics and microelectromechanical systems, again, MEMS. So Dr. Zhao is going to talk today about portable flow cytometers.
Portable flow cytometer. Over the past 60 years, flow cytometer has become the most powerful instrument for bioparticle analysis in this world. More and more new techniques have been created, such as spectrum detection, imaging, and high-speed sorting. But flow cytometer is still the instrument which should be carefully maintained in the lab and operated by the highly skilled professionals. It's time to think about the next. What is the future for flow cytometer? The answer is portability. Why the portability must be the future? Let's go to review the development of computers. At first, the computer was so huge and so heavy that it can only be used by professionals for some high-value works. Then we had the desktop, with which we can process documents at our home. Next, we have the laptop, and we can take it to anywhere. Today, with smartphones, anyone can enjoy the digital computation-based modern life at any time and anywhere. The more portable the computer is, the more people can get the access to digital life. Eventually, portable computers change everyone's life fundamentally and reshape the whole human society. That is the power of portability. With the same logic, the portable flow cytometer must be the future with the ability to benefit everyone's life. For example, during the pandemic, people have to send their samples to the lab for COVID-19 tests and have to wait for 1 day to get the results. During this waiting period, the positive people will not only spread the virus, but also lose the valuable time for treatment. Well, if we have a portable flow cytometer, which allows the test right here and can give the result right now, it will save countless lives. Our target is to build a portable and smart flow cytometer, which can be easily operated by anyone at any time and anywhere. But how? In general, flow cytometer contains fluidic system, optic system, sorting system, and electronic system. The key is how to minimize the fluidics, optics, and sorting systems. The traditional fluidic system is huge, contains many components. We integrate the fluidic system into a microfluidic chip, where the sample flow is focused to be a narrow stream along the channel center line at a speed as high as 5 meters per second or even 10 meters per second. allowing up to 50,000 bioparticles to be measured in 1 second. The optical system is for laser illumination and light detection. Our solution is to design a diffractive optical element to simultaneously convert multiple lasers into flat-top beams for laser illumination. In comparison, the traditional beam shaper is contracted by many discrete optics with a huge volume and low stability. In addition, we are studying the on-chip spectrometer to complete the fluorescence spectrum measurement on one small chip. The traditional slotting is finished in an open space in a way similar to the inkjet printer. This system is not only big, but also generates aerosols, reducing the biosafety level. We created a microbulb sorter and integrated it into the microfluidic chip. As shown in this video, every second, more than 1,500 target cells can be selected from the sample flow in the totally enclosed metal channel. We have developed these fundamental building blocks for portable flow cytometer, and we will do our best to make the portable flow cytometer come true. We believe one day portable flow cytometer will lead us to a future where professional measurements of immunology, hematology, and oncology are accessible to anyone at any time and anywhere. It will empower people to comprehensively monitor their health weekly or daily at the molecular level, rather than the annual physical examination at the hospital, or that when you feel too bad, then you go to the hospital. Usually, that is already too late. Portable flow cytometer must change the healthcare revolutionarily. We are a team from Tsinghua University and Stanford University. You are very welcome to contact us. Thank you.
Now again, another fantastic talk. Just a reminder that if you have questions or you want to, as Rob was saying, initiate a conversation with any of the speakers, please do so through Slido, and you can pop your question in there and reach out in a way. So this is also a networking session. Obviously, we cannot be there in person, but then we're trying to use Slido as a proxy for that sort of interaction. So please do. Now we have a fourth speaker. Is the last speaker of the recorded presentations for today of the innovators before we start with the actual presentations. Live, I would say, live presentations. So to the fourth speaker is Dr. Kirk Moutafopoulos, if I pronounce it correctly, and who is currently the director of R&D at Cytonom, and he's also a research associate at Harvard's School of Engineering and Applied Sciences. But also he is member of the ISAC Innovators Program that you all are aware of it. So his interests include microfluidic-based medical diagnostic tools, in vitro fertilization devices, surface acoustic wave applications, imaging, and machine learning. And today he's going to talk us about the future of microfluidics for cytometry. Over to you.
Hi, everyone. My name is Kirk Moutafopoulos. I'm an ISAC innovator. I'm the director of R&D at Cytonom ST, and I'm a research associate at Harvard School of Engineering and Applied Sciences. This brief talk will be about the future of microfluidics for cytometry. It's a tiny technology with a big future. So microfluidics is a technology. For microfluidics to be valuable in the future, it's going to depend on transformative organizations, a lot of labor, capital, materials, and information. It's going to need to be very disruptive technology, and I think it's only just begun to make a big splash. Its presence in mainstream commercial applications is growing, and I think we're going to see a lot more of it in the years to come. But why isn't every cytometry lab littered with commercially viable microfluidic devices? Well, I think the three biggest reasons are PDMS devices only get you so far. There's been a heavy leaning on using PDMS devices. Don't get me wrong, they're a great proof of concept and great for minimally viable prototypes. But once your paper is published, how often is that PDMS device being used? And if you want to go and commercialize that device, what are you going up against? Well, you're going up against prohibitive costs. The manufacturing industry for microfluidic devices is still quite expensive, even at the prototyping scale. Believe it or not, the average cost per prototyping run can range from $60,000 to $200,000 US, and large volume orders are needed to lower that cost. It also takes time. Lead times for chips can be 3 months or more. Complexity of the device and its features can impact the capabilities of the manufacturing company. Overall, if you're looking to make a complex, multifaceted microfluidic device, you're looking at spending a lot of time and money just to get there. On the other hand, if you're making a really, really simple device, you can get there pretty easily, maybe on a shorter time span, less cost, but ultimately you're not really going to be innovating and creating new techniques and applications for cytometry. I think the global microfluidics trend is growing. According to some market research, it's almost going to hit nearly 60 billion by 2026. And really what's starting to drive the market is the pandemic, increasing adoption of microfluidic devices, and the need for miniaturization of laboratory equipment. They're all kind of somewhat interrelated. Microfluidics is almost everywhere. It's in a lot of places outside of cytometry. So just for reference here, when someone says, oh, I don't think microfluidics is going anywhere, well, if you're a cytometrist, you may feel that way given the innovations and the need for other innovations to happen, but it's here to stay. And I think there's going to be a lot of revenue to come from these outside cytometry sectors. But what's important is the revenue generated from microfluidics outside of cytometry is ultimately going to bolster and support those microfluidic chip manufacturers to support the needs of cytometrists. So microfluidics and cytometry. Again, microfluidics is almost everywhere, but there's also a lot of microfluidics cytometry companies out there, and this isn't even showing all the companies out there. But what's even more fascinating and more important that everyone should be aware of is that the number of prototyping and manufacturing companies are growing, and those companies that are currently available on the market are growing as well themselves. They're growing in size. The features that they can go down to, or the different geometries they can make for microfluidic devices are growing. Their ability to integrate electronics, other microelectrical mechanical systems, optical elements is growing, and these companies are able to start making more and more sophisticated microfluidic devices. And that ultimately is what's going to help drive the future of microfluidics for cytometry. And so when I think about all this, I think about what are the 3 key features for microfluidics for cytometry for the future. That's sample preparation, sample detection, sample separation. For sample preparation, we're going to need large-scale passive or active debulking devices. We're going to need them to process large amounts of samples, large cell concentrations. I think we're going to be seeing a lot of devices that have that support on-chip labeling and wash steps. I think we're going to see a lot of devices that are prepping the sample for downstream sorting, and we may even see those sorting devices on the same chip that's prepping the sample. I think for sample detection, we're going to start seeing a lot more devices that have embedded lenses and optical elements in them. I think these chips and these devices are going to be taking advantage of a lot of imaging technology around there, and of course, integrating your MEMS components. Hopefully, these devices will start supporting label-free detection, and I think we're almost already there, and ultimately, parallelization is going to be key for the future. And that similarly goes for separation. Parallelizing sorting channels to achieve high throughputs, faster sorting mechanisms, high recovery, high purity sorting in tandem, and incorporating multiple MEMS components on a single chip needed for separation. So what will a future microfluidic cytometry device look like? I think it's going to be complex. I think you're going to see different types of sort switches in tandem, maybe optical elements, maybe electromechanical elements. I think they're going to be supporting large sample concentrations. Ultimately, microfluidics needs to hit the numbers that jet and air sorting can achieve, and ultimately support imaging and machine learning for cytometry. I think that's going to be a big push. Just real quick, this is just some information about me. I have about 10 years of microfluidics experience. I've been in multiple microfluidics labs, and I currently work at Cytometer. Here's briefly just my contact information. Feel free to reach out and talk more to me about what you think the future of microfluidics might be.
Fantastic. So now we are moving into the first of our live presentations. And it's a pleasure for me to introduce here today to this Innovators Workshop to Dr. Arnold Yu. He is a ARC DECRA Fellow, and he recently started his lab at the School of Biomedical Engineering and Heart Research Institute at the University of Sydney. He's received a number of awards and recognitions, and his main focus is the cardiovascular mechanobiology, where he's implementing a research program here at the University of Sydney. So today, Arnold, and I can see that you're already there, all ready to go, he's going to talk about biomembrane force probe for future of single-cell mechanobiology cytometry. Take it away, Arnold.
Thanks, David. Am I loud and clear?
Yes, all good.
Oh, good. Okay. Thanks. First of all, I'd like to thank the ACS, particularly Rob, for inviting me. And I really appreciate this opportunity to join David and Majid and also all these fantastic colleagues here. So I'm going to talk about the titles, biomembrane force probe for future single cell mechanobiology and cytometry. So first of all, I would like to start with this video to highlight my research and then to give a 30 seconds introduction.
Each year, approximately 55,000 Australians suffer a heart attack, many as a result of blood clots. By analyzing the mechanical forces in molecules and cells that drive blood clot formation under flow circulation, I have pioneered the bioengineering techniques to diagnose, treat, and control the blood clotting diseases. Using the mechanobiology to advance the knowledge of cardiovascular system at molecular and cellular scales, I discovered mechanosensory proteins and developed mechanomedicine to prevent the disease-forming clots.
So I've been working on single-cell mechanobiology approaches for technologies for the last 10 years. So this is a very exciting but also challenging journey. We've seen this many single-cell biomechanical nanotools has become available over the last 10 years and has been used to discover how the cells respond to the mechanical forces. But the problem with these technologies, they're not cytometry grade. They're low throughput, they're labor intensive, and they're very bulky for their setup. On the other side, in the thrombosis and the cardiovascular areas, one of the most successful preclinical and commercial applications in the last 2 decades is the flow cytometry. And as we started this workshop using the Slidos by Rob, and we see that the flow cytometry has been widely used for cell countings, the cell cycle analysis, detections, and most importantly, and for cell marker characterizations. The only things that flow cytometry so far has missed, in my humble opinion, is that it doesn't well consider the mechanical force factors with the traditional conventional flow cytometry setups I'm talking about. So it is a little bit difficult to directly apply the flow cytometry to study the mechanosensing or mechanobiology. So this is why today my talk is trying to demonstrate what we're trying to do to combine the biomechanics with the flow cytometry. So this is the technology I've been working on for the last 5 years. Setting up the first of these setups in the Charles Perkins Centers at the CPC. So this is a micropipette-based cell aspiration assay, and we attach these things by immobilize the beads on top of the aspirated cells, which is the red blood cells, and we can make this as the force probe. So what is a BFP or force probe, biomembrane force probe does is to use this to probe the proteins on the cells, and then to look at how they respond to cells and then change their functions. So this is really relevant to our new knowledge on understanding how platelets, particularly the blood clotting cells, respond to shear forces and then leading to the thrombosis. So what it does is an excellent biomechanical nanotools for 2D kinetic measurements at the cell-cell interface. So by using these engineering technologies to program these mechanical impingement, we can apply the BFP to characterize how the single receptors integrins on the platelets and how they function to mediate the platelet adhesions. So the truly strength of such a system is that you can apply this to the primary cells and to probe their adhesive behaviors with the high sensitivity, precision, and high dynamic ranges, single molecule biomechanical kinetics measurements. And we apply this and upgrade this into a 2-force probe system so that we can look at the signaling and the mechanical couplings between 2 receptors. In this case, we published Nature Materials paper to look at the integrins responsive to the mechanical forces on platelets. So the take-home message is the importance of the BFP and apply the precisely controlled mechanical stimulations on single cells, as particularly the primary cells. And we can identify these multiple conformations of these receptors on one of these cells. and how they respond to mechanical and chemical stimuli. And following that, we also explore the application of such biomembrane force probe to therapeutic evaluations with high accuracy. So there are two systems we're looking at. The first of all, of course, is the platelets. We look at the several anti-thrombotic drugs and look at how their effect works on the single platelets. So this has been published, and we're looking at this a clinical trial inhibitors called AZD6482. We look at how these things can change the integrin functions in response to force. And actually, the clinical data, preclinical data suggests our characterizations with BFP really help them to understand how this PI3 kinase inhibitor inhibit the platelet functions in arterial thrombosis, where the shear stress is very high. And the second part is we look at this using the BFP to look at how the BFP can be used to characterize several PD-1 antibodies. So this is a very exciting area for cancer immunotherapy. And how this PD-1 antibodies or PD-L1 antibodies, how they work and to inhibit the cancers, it has not been well characterized. So that's why we apply the BFP to look at the cancer cell and tumor cells interactions. And we also look at how mechanical forces affect the PD-1 function. So this is the data that we published in the Nanolighters, and then we show these mechanical characterizations is really important for us to screen the best anti-PD-1 antibodies and for cancer immunotherapy. So we've seen these, and we observed the emerging commercialization potential for all this the automated biophysical nanotools in the last 3 years, and we've seen lots of these new companies actually emerging, from the Impexus Lumix, and now to see there's several setups that people automate these biomechanical nanotools, optical tweezers, AFS, cell avidity analyzers. So. But what really I think is not enough is so far the throughput or these miniaturizations has not reached to the cytometry level, and I think this is a very exciting areas that we can give a further push to make these biomechanical nanotools, the commercially available nanotools, into a cytometry grade. So I think the key is to have the artificial intelligence and the microfluidic automations. And this is really the important things. That's why I'm presenting this next steps with my new labs. We're trying to integrate the artificial intelligence and microfluidics fabrications to achieve a cytometry-based a biomembrane force probe. So that's what we're trying to do now. And we're trying to integrate the micropump, microlens, and the BFP onto the chips and combine with the image-based AI. So thank you very much. Again, I would like to acknowledge all my colleagues and collaborators, and also these fundings from ARC and NHMRC. It's very difficult nowadays to secure these opportunities, but I think I've been lucky enough, and that this luckiness cannot be achieved without the collaborators from UCID, my groups, HRIs, and also long-term friends from Helen's Hongxi and Peter Su from the Sydney area. So thank you very much. Thanks, David.
Thank you so much, Arnold. That was a really good, very interesting research. Now, as this is a live question, we have the privilege to have Arnold here today. So I open questions for Arnold at the moment. Is there anybody? So please feel free to unmute yourself and ask the question. Or otherwise, if you want to, you can also pop them in the chat, and I will be organizing them as well. In the meantime, I actually do have a question. I mean, your research is very provocative, and I think that those interactions that you were showing with the PD-1, PD-L1 interactions, how important is mechanobiology to understand those interactions, and what are the consequences for drug screening? How can we harness those interactions for our advantage of characterization of the responses to the therapy, or to the responses or the interaction between the cancer cell and the T cell? Now, as I understood, you have basically this is a cell-to-cell communication in a cell-free system where you manipulate the cells to be together, and then you can study these mechanical properties. What do you think about doing this in a three-dimensional space where you have, for example, an organoid, and then you can target specifically a couple of cells that they are together, very close together, and can you sort of try to understand that sort of dynamics and that connection?
Yeah, David, that's a fascinating question. I think, we're talking about two important things in the field. So the cytometry-based method, people usually ignore that or kind of underestimate that. The problem is you have to isolate the cell from the living tissue or living microenvironments. So when you isolate the samples, the things change. So that is why, when we when we publish that nanoletter papers, there is actually quite controversial discussions that the PD-1 effect, how the PD-1 antibody, how this and the blockade checkpoints series, that a lot of these things, people discovered or, set up the clinical pipeline trials, they're in the isolated environments. So they need something that, they can do this in the native environments with the niche. So that's certainly, very important to have the system, as you said, 3D, a real microenvironment mimicking system. So, and the second thing is, it's also come with my recent collaborations with UT Southwestern, that people talk about this. The stem cells works, they use a lot of cytometries, but what they find is the intravital microscopy when the animal is still alive, or they do this, whatever the discovery they made. When they switch to the cytometry system or the stem cell culture system, everything changed. So basically everything in the in vitro does not match well with the in vivo data. So that calls for another thing is, I think, 3D native environment, the whatever cytometry system, if we can do in that kind of environment, that would be the final killer. But the thing is, there is not I don't think the technology is there yet. So I think it's better to use something like spheroid or it's organoid. I think this is a very good compromise. I see these things rapidly evolving. So that's what I'm trying to collaborate more, in the senior areas, and we can put. But what my interest is the mechanical forces. So I think that is important. But I also think in a large sense, cytometry society need to be more embracing this as new technologies, new ideas, rather than you just do the traditional way, isolate the cells and put them into the tubes. I think this is changing.
Yeah, thank you. I'm very happy to hear that from you as well, because this is exactly what I think. And this is, I think that, like all these other components, like extracellular matrix and all those other components that we are not taking into account when we put cells in isolation. I mean, it's a good start. It's good, it's high throughput, but I think that understanding the cells in their own specific niche will be the ultimate goal to, moving forward. So, and as you said, organoids is a very good compromise in there to develop all those techniques before moving into the in vivo sort of systems. Helen, do you have a question? It seems that you're coming up. Hi, Helen.
Hi, everyone. Not a question so much as a comment, and obviously, Arnold, I think your work is amazing, and I think this is really like pushing the boundaries. And when you were going through your talk, it kind of reminded me of how the field of imaging flow cytometry developed, and now that is so commonplace. So maybe this is kind of the next iteration of how we think about imaging flow cytometry, and just bridging all of the omics and everything. It's great.
Yeah, I definitely think we should talk more, Helen. And I think the pandemic doesn't really help, but yeah, I really agree with you and David, that one person can only do one job. So, but if we like having these interactions, I think we're gonna see better things coming out.
I've got a quick question.
Yes, go ahead.
I'm very great talk, Arnold. That was really, really exciting. But just wondering, like, will that kind of technology be eventually evolve? Do you foresee it evolving to a stage where, instead of having two probes on opposite ends, having that connection and having the signals and detecting signals. Do you foresee this as a form of initial development where it will eventually be able to, say, probe into an actual, say, tissue where the cells are in the actual environment, not dissociated, where then a probe can then go in and probe the various cells at their specific environments, and then detect changes and how they perform and things like that, rather than looking into actual having to dissociate a single cell before you test each cell out kind of situation.
Yeah, thanks, Eric. So that's a very good point. I think there are two issues here again. So I think that the first of all, moving from cells to tissues, technically I think is getting there, and there's just a lot of the technology in place. I think it's time to put them together. But my concern with the directly working on the tissue is the heterogeneities and the reproducibility. I think I've been working with thrombi. Thrombi is a tissue, but when you work with thrombi versus single platelets, and you observe there's a very wide heterogeneities of the studies. So then, which means making the data interpretation is very difficult. But if you look at all this, like Helen is running CyTOF, at the UC, if you look at all the CyTOF papers, it's such a heterogeneous, the data samples. So you need a very strong data scientist or statisticians, to really actually help us to interpret the data. So that's something I concern, and I'm hesitating to directly jump from single cell to the tissue level. But I do think the technology is available. And the second thing is I've been fascinated by this AI. So I actually think, if we can have the AIs, so even we do single cells, so what? And the computer will do it for us, just count one by one, like the computer counted. So that's kind of what I'm trying to give a push from that perspective. I would like to stay in the single cell and then do some AI works, rather than I bring the whole program to the tissue side, but I think, talking with David, I think, having complementary setups on the organoids, on the spheroid, I think that's going to give another line of evidence for whatever we propose. So I think in that approach, I think, push the single cell, but in the meantime, develop complementary collaborations on the tissue levels, working with the tissue people or intravital or animal in vivo people. I think that would be the solution.
Great. Majid, I saw you turning on your camera. Do you have a question?
No, I just wanted to, again, detour what you guys are saying. We need to really think of, probably as an outcome of this conference, think of a scenario of desynchronized experimentation at tissue, spheroid, aggregates, and organoids level. And probably a big, I don't know, synergy type grants that we look at the spectrum of things, seeing with all these tagged antibodies that they are now available and heaps of equipments that is around us. And of course, the emerge of this special biology, things that you can do with nanostring at the tissue levels, hundreds of the tagged antibodies. Somebody should look at these things in parallel, right? And as you said, we get native tissues and then break them down to the single cell levels and look at all this spectrum of the things. And the things that Arnold was showing in context of PD-L1, I guess, is highly true. It's a very, very dynamic protein, and you cannot, stuff that you are thinking getting out of the single cells is not probably applicable inside the original tissue. And this is what we see in our experimentation too. I just wanted to detail and say that this is true, and probably we could have Rob could synergize probably an outcome of this conference at the ends, that we see what we can do in the futures and how we can apply for one of these gigantic grants to address these challenges, issues as we discuss.
Yeah, we need a synergizer.
Thanks, Majid, for the comment. I think that is great, and thanks, Arnold, for your presentation. Has produced some interesting discussion, which I think that we can follow up a little bit on the panel discussion at the end. I think this is a great opportunity for us for this exactly, networking, and try to see, from these, all this expertise, all this beautiful research happening, what can we do to bring it together and then move to the next step, right? And then next year, at this time, we have another conference with all these outcomes that, you know, that this sort of connection between different research fields have brought together. So I'm looking forward to seeing that. All right, that's fantastic. So in the interest of time, we're going to move to the next live presentation. And this one is Stephen Vasilescu. Hopefully I pronounced it properly. He is a current CEO and co-founder of Microgenesis, which is a medical device company developing technologies to improve the outcomes of reproductive treatments. Stephen is currently focused on improving DNA integrity of sperm cells and idiopathic male infertility and the isolation of rare sperm cells from testicular microsurgery. He's also doing a PhD at UTS with Majid. Very exciting to hear what is he going to tell us about. I think he has a very interesting angle to share with us, and it's all in the title of his presentation today, My Startup Journey in Australia, Microgenesis. Over to you, Stephen.
Thanks, David. Can you guys hear me okay? Can you see my slide?
All good, thank you.
Perfect, awesome. Yeah, thanks, David. And thanks, Rob, for inviting us to present a little bit about our startup. It's always very exciting when we get to talk about what we do and then see how we can collaborate with people to make better technology. Hi, everyone. My name's Stephen. I'm the CEO, and along with Majid and Sajid, who are also here today, a co-founder of Microgenesis. So Microgenesis is a medical device startup developing technology to improve the efficiency and reliability of fertility treatments. So today I'm going to talk a little bit about our vision, our technology, how we got here, and I'll talk a little bit at the end about flow cytometry in gamete research, what we've been looking at. So a bit of background, according to the WHO, infertility affects 1 in every 6 couples. It's roughly about 16% of all couples have a fertility challenge. But historically, the onus of infertility has fallen on women, but this actually isn't the case. In fact, over 55% of the time, infertility involves a male factor, and about 30% of the time, infertility is solely the cause of a male factor. But the way we treat male infertility in particular has undergone very little technical innovation since the 1980s. And unfortunately, IVF success rates have stagnated in the last 10 to 15 years or so to about 33% for each cycle that has an embryo transferred. It's actually closer to 19% success rate for all IVF cycles that start, which is not what you see advertised by the fertility clinics, but it's quite a low success rate, and it's quite staggering. So our mission is really to bring some innovation to the front of reproductive healthcare, particularly in those areas that perhaps are a little outdated. So we realized quite early on, starting from UTS, working in Majid's lab, which has been terrific, that understanding the IVF market and how they operate was crucial to developing new technology and selecting the problems that we want to tackle. So this is a major tip for anyone considering a startup: is customer validation sets you up for success. You don't know your value proposition until you speak to dozens of potential customers and clinics, and doing talks like this where people can come to you and tell you how you can make an impact. So it really informs your business plan, your regional markets that you want to hit, and how you want to validate your technology in particular. So we began quite early on by partnering with IVF Australia, Peking University in China, Monash Hospital in Melbourne, which is where I'm actually right now. We're running a clinical study, which is, I'm happy to say, is going very, very well. And only by getting into these different centers, we're able to hone in on how we can best improve IVF practice, in particular gamete preparation, which is what I'm going to talk about today. So we realized that while IVF has helped millions of couples start a family, an essential component to all IVF treatments is sperm selection, which is what I'll be focusing on today. But conventional sperm selection is fundamentally flawed. Gold standard techniques such as density gradient centrifugation and swim up, which is another centrifugation-based technique, apply huge mechanical forces that damage the DNA of sperm cells, which struck us as quite odd, because you want to choose the healthiest sperm for IVF in an already compromised pair of individuals. Why are we using that techniques that inherently compromise the chance of success by inducing damage? The sperm selection process is also labor-intensive process. It's very prone to human error. different clinics, even within the same other company, do things totally differently. And they have extended labor costs, particularly when you're working with less experienced technicians. So all of this results in poorer quality sperm selection, which can directly contribute to lower embryo quality, lower implantation rates, and a higher chance of miscarriage, particularly when you're talking about using sperm with fragmented DNA. And I'll talk a little bit more about that later, how we validate fragmented DNA. In fact, studies show that using sperm with fragmented DNA can more than double your chance of a miscarriage. So the very first step that you do in the IVF process, where you're doing your gamete preparation, heavily impacts the success of the whole treatment. Like I said, I'll talk about DNA fragmentation later. Surprise, surprise, we use flow cytometry, if you haven't already guessed. So basically, we need to take better care of our sperm, and that's where our startup Microgenesis is here to do that. So we use our microfluidic technology to reframe the way we select sperm cells into a more safe, reliable, and efficient device that we're calling the IV Micro F. You can see a picture of it there on the left. So the device itself didn't happen overnight. It actually began with our co-founder Reza and his work in understanding sperm migration through the female reproductive tract. Before we realized we could leverage that behavior to not only select sperm, but resuspend them in nutrient buffers to sustain their performance over time. And even then, going from there, everything worked well, academically, but working in a clinic is a whole nother ball game. So, following the saying, if something can go wrong, it will go wrong. So for us, we've used all of our collaborators that I mentioned, I think, really quite well to optimize our device to fit with the IVF workflows for things that you wouldn't even be able to think about. And then you have to start thinking about the volume of sperm, the concentration of sperm that they need per egg. They need about 50,000 per egg, but they can get anywhere between 2 eggs and 30 eggs per treatment. So you never really know. You have to be really, really flexible. But now we have a device that outperforms existing methods of sperm selection, not only in terms of time and ease of use, but also in terms of sperm quality. It allows clinics to complete their sperm selection within 1/6 of the time, but without compromising the treatment like conventional methods do. And we're keeping this technology simple to use. Limiting the number of steps is something that we've been really conscious of, because we know clinics won't adopt the new technique if it negatively impacts their workflow. So our technology is biologically inspired microchannels that mimic the environment inside the female reproductive tract that sperm naturally have to navigate. We're also developing a further generation capable of selecting sperm based on externally expressed proteins indicating apoptosis or early stage apoptosis. So our device provides improved sperm vitality, motility, and DNA integrity, which are all essential components of a healthy embryo. Where conventional methods at most will provide a 30% improvement in DNA integrity, depending on the method you're using. DGC actually typically increases the amount of DNA fragmentation you get. Our device provides an over 80% reduction in DNA damage, giving you a sperm population with the highest prognosis category for DNA integrity, which is a predictor for success down the road. Next slide. This is normally where I make a joke about not being able to do a live demo, but videos work just as well. I hope you guys can see the video. So here you can see the result. All the sperm free of contaminating cells, plasma, and so on are on the right. On the left is quite a really terrible raw sperm sample with all these contaminating cells, epithelial cells, white blood cells, dead sperm, and what have you. So the device uses the inherent nature of the sperm motility. We give them a lot of guidance. It kind of ends up being like the sperm Olympics, basically, to select those sperm and put them in a nutrient buffer and remove them from all of the cells that you don't want. So leading up to this, our technology was grounded in years of fundamental research, lots of publications to sperm motion and selection, like I mentioned. Our startup journey began with us winning the UTS Accelerator program in Sydney, which is great from the sense that our advisors from Fishburners pushed us through customer discovery really early. Over the past year, we've spent a lot of time working with clinics, making them strategic partners, validating our device, working towards our MVP. We've also made a point of understanding the regulatory requirements of our technology, which is a Class 2A medical device, which in itself is another tip for anyone wishing to do a startup in medical devices. Know the regulatory requirements for your region and don't underestimate the timeline. Even though our technology is relatively simple compared to other ones, we have future geometries which are more complex. It is a lot of time and capital that you need to put in. So bring on, another good tip is bring on medical and industry advisors really early on to diversify your team. And we have a terrific team. So now we're at a very exciting stage of where our clinical validation is rounding up. We just finished an accelerator program, or finishing in a month, an accelerator program called the ICP in Singapore. Actually, we just, Sajid and I just won for this work the UTS FEIT Excellence Award 2 days ago, which was really good to see. So we built a terrific team around us. Majid, you already know. Reza is a biomedical science specializing in microfluidics for fertility. This is our business team, Juan, David, and our advisors down the bottom, David Sinton, who's an engineer from Canada, and Hisham Mara, embryologists, experts in reproductive healthcare, and their advice has been invaluable for us. So now I said I'd talk a little bit about flow cytometry for sperm, and it actually plays a critical role in our evaluation of sperm health. So selecting sperm with the highest level of DNA integrity, is the biggest benefit of our technology because it plays a huge role in embryo development and by extension, pregnancy outcomes. So the gold standard method for DNA analysis is a sperm chromatin structure assay, or SESA, which is a flow technique where we're using to detect breaks evaluated indirectly through DNA denaturability. So the assay measures the susceptibility of sperm DNA to acid-induced DNA denaturation in situ. So followed by staining with fluorescent diacridine orange. While the alternative techniques are typically only a manual count under bright field microscopy of about 300 or 400 sperm, the flow cytometry lets us do anywhere between 5,000 to 10,000 sperm in a much less subjective manner. So that's why it's the gold standard. Not only do we get a scatter plot of the red and green sperm for a DFI box plot, like here, you can see on the bottom right, starting DNA fragmentation. In the raw sample, we get a little bit of a drop from one of the conventional techniques, but we get a quite dramatic drop from our device, which is terrific to see. But also we get the sperm with the most intensive green color. We term them high DNA stainable sperm, or HDS sperm, which is thought to represent immature sperm, but we don't actually know if that's true. So it becomes very interesting for us. And this is where I think flow cytometry can make a little bit more of an impact, and there needs to be a little bit more investigation. We don't actually know what these values mean in terms of fertilization capability for the sperm. So it's still unclear about the precise mechanisms and types of DNA damage that are lying behind these values that we're getting. So we think that DFI is related to the percentage of sperm with DNA breaks or protamine defects, but we're not quite sure actually. Then you've got really 4 key areas that you see clinically with lots of clinical relevance in terms of cytometry, where we're looking at reactive oxygen species, or ROS. Reactive oxygen species, the primary driver for DNA damage. So being able to detect reactive oxygen in semen, or detect if your separated sperm or your media, your process is inducing a release of reactive oxygen is really, really valuable. So we're also looking at negatively selecting sperm through the externalized expression of apoptotic markers using microfluidics, which we again characterize through cytometry. One of the bigger mysteries in fertility is, why do we need 50,000 sperm to fertilize 1 egg in vitro, but in vivo we only require 200? And what we're finding is that conventional methods of sperm selection actually increase the incidence rate of sperm apoptosis, even though the conventional sperm metrics of just motility, morphology, how they look to the naked eye basically say that they're good. What we're finding is actually they're on their way to degradation, and that directly affects their motility and their fertilization capacity, but it's not part of standard evaluation. So doing this type of validation gives us an added metric for, and another dimension for predicting the success of how a sperm is going to perform. So what we're really looking at is trying to marry some of the cytometry with our microfluidics to create better technology and observe new behaviors that we could leverage. It's still quite a very early stage for us understanding sperm behavior. One thing that is really, really interesting is what I've got there, the sperm membrane integrity, acrosome integrity, and mitochondrial function. So when sperm are going through the female reproductive tract before they reach the egg, they undergo a whole suite of chemical changes that happen quite quickly. So their membrane permeabilizes, they have a massive influx of calcium, and that hyperactivates their motility. Then their head of the sperm gets exposed, the acrosome gets exposed so that it can fertilize the egg as well. But measuring these and how they make those changes is actually quite difficult. And what that means in terms of clinical relevance is also quite new. So I think there's a lot of work to be done in terms of cytometry, particularly at a live kind of level, where we can track the sperm's changes and try and marry it again to some sort of behavioral characteristic for selection. And the other big one, of course, is sperm gender selection, which we look at less so in the human side of things, more so in the animal market. When you're talking about animal husbandry, the best way is with a type of host staining. So the X, the female chromosome, stains brighter because the material is a bit more dense. However, that becomes a bit of an issue again, because you're directly staining genetic material, and then you're relying on that same genetic material to fertilize an egg and then create a healthy embryo. So there is a lot of work to be done there, but there's been quite a lack of innovation in that space as well. So thank you for allowing me to present. We really do believe that innovation is, the future of IVF, and doing talks such as this really help us collaborate with some really interesting projects. If you guys have any questions, I'd be happy to answer.
Well, thank you very much, Stephen. That was a very, very interesting presentation that incorporated the journey together with a bit of the technology coming together, and delivering very interesting outcomes for the market of IVF. And thank you for the educational also way to show us, what are the critical factors for a correct sort of a sperm preparation, and what would be the parameters to look at the selection of that sperm. So I'd like to open the floor for questions, but before that, I do have a question. And I think that perhaps, this sort of recaps as well, like, what have you been suggesting in your talk? Well, at the moment, I mean, you probably use flow cytometry as a testing method, just to test if your DNA is correct, but you're not using it for selection, because that would probably damage further the sperm. So looking at this innovators sort of program where you can incorporate that selection together with your device without damaging, but also quantifying that in a one go, I think that will be quite beneficial to get to that selection. And you're also really talking about multidimensional sort of characterization of the sperm. So this, you mentioned DNA fragmentation, motility, membrane stability, a few things that obviously you can think on a kind of a device that multiplexes all these parameters and then gets all the measurement in one go into your whole sample. So, it's not a sampling, that you take, a few thousand sperms to look at what is the integrity, but you actually do it in the whole sample. So your levels of, I guess, certifying the quality of your sample will be, increased astronomically. So, looking forward to see, what people in this room has to say about, the possibilities of that, looking to incorporate that into the future.
Yeah, that'd be absolutely terrific to be able to look at all of those metrics quite quickly. Would be amazing. And obviously when we're talking about semen samples, we're talking hundreds of millions of cells that you have to process, and finding the right one or the right, dozen for that many eggs can be quite a challenge. And the level of variety and heterogeneity between sperm is absolutely immense.
Very interesting. So is there any questions? So again, I got Arnold, do you have a question?
Yeah, thanks. Thanks, Stephen, and also Majid. I think this is very exciting translational works I've seen. So I would like to ask you, just related to microfluidics, I think the engineering question is the cost. How are you gonna? I guess just it's something I'm trying to ask is how, or comments is how this thing can be, the cost can be reduced to generate. I mean, I assume this is a one-time use device. So how are you gonna, how these things can be dropped down to certain costs that they can be like really game changers? This is something I would like to ask. And what do you think of so far? And this, can you think something like below $10 or maybe $2 that kind of these things can be done very quickly?
That's a great question. You're right. I mean, the cost is hugely important. And it is a consumable device, obviously you don't want to be reusing the same device between multiple IVFs. But it becomes quite complex because there are different types of IVF depending on the severity of the fertility that you're talking about. So when you're talking about cost of goods and manufacturing the devices, it becomes quite cheap because there aren't too many functional components in there. So we're leveraging the inherent motility of sperm, giving them a lot of guidance. So cost isn't too much of a factor, but cost for the clinics becomes a question of scale and the type of fertility that you're talking about. So there's a similar product on the market, Zyma, that I think they're around the $150 per device range, which the feedback from the market is actually that's a little bit too expensive. But when you think about it in terms of conventional methods taking you, an hour plus to do the processing for one sample, and you can't parallelize it, where ours takes about 15 minutes, you're saving a lot of labor. And that frees up the technicians to move ahead, go to the egg processing side, which is happening live. They do the sperm preparation and the egg collection at the same time. So they have to be quite versatile. So there's costs in terms of that. So it might not be something like $10, we're looking about $60, $70 per chip. But again, it comes down to volume and the region as well. Right. We found that how sperm selection is done in Asia is very different to how it's performed in Australia or Europe.
Yeah, that's right.
So there'll be a lot of region specific, play there.
There's some superstitious factors there as well, I suspect.
Oh, 100%. Even amongst the clinicians, it's quite baffling, actually. But being able to do, like David mentioned, and like Kirk mentioned as well in his talk, a more robust method for analyzing all of these different metrics would be absolutely fantastic, because what I'm seeing now, even the clinics that I'm working with, it's very, very rudimentary, and time is of the essence. That's the other big thing. They're not doing a lot of characterization before they want to do the fertilization, because they want to keep the sperm out for as little time as possible. They want to get it into the egg. They want to put it in the culture and get it going. They don't want to leave it out for too long. So speed is a really big factor as well.
Yeah. Thanks, Stephen. And Majid.
Thank you.
Thank you. That's great. Rob, you had your hand up and not anymore. Do you have a question, comment?
I did. I think the time is running away from us. But Stephen, in this sort of idea of integration, my understanding of this device is you put the sperm in, they travel up the channels, and then you take them out and you process them. I wonder whether there's a step in there that you can actually just put the egg inside that selection chamber to see whether or not that will actually improve your fertilization rates.
No, definitely. And that's such a great idea. You've actually hit upon the next part of my thesis. So
I wasn't aware of that. That wasn't a leading.
No, definitely. And that's something that the clinics are also very keen in. The trouble is definitely in terms of standardizing the IVF workflow and combining workstations. It's a terrific idea. It becomes quite tricky though when you're mixing the oocytes and the amount of time you have to leave for fertilization. You really want to control the number of sperm you expose to each egg, because if you do too few, you're not going to get a fertilization event. If you do too many, you risk what's called polyspermia, where you get multiple sperm entering the egg at once. Remember, we're dumping 50,000 sperm per egg. In nature, you've only got 200. So we're already at a really high risk of multiple sperm entering the egg, and then there's not enough genetic material from the egg to go around, so it dies. So this is where, again, like Arnold mentioned, having a little bit of AI, or not even AI, just computer vision to map and control how many sperm we get through becomes really, really important.
Interesting. Thank you.
Thanks.
Fantastic. Well, thank you very much, everybody and all the speakers. Now we're going to continue with our recorded talks, and now I'm handing over to Sajjad to present the next set of speakers for the video presentations. Sajjad, all over to you. Thank you.
Thanks, David. I'm really glad to be here. Many thanks for Rob to inviting me. I'm really excited to see many of my friends in the participant list. I hope you all enjoyed the workshop today. The talks were really great. Actually, we learned a lot so far. So I would like to introduce the next four cytometry innovators. The first one is Dr. Takeaki Sugimura. He has more than 10 years of industrial experience in hardware and software development of imaging systems, including image-activated cell sorting technology. Also, he was selected as one of the first ISAC innovators in 2020. To those who didn't see his great article that was published in Cell Journal, I really encourage you to have a look. The follow-up articles have been published in Lab on a Chip and Nature Protocols. Those articles are really great. So let's listen to his fascinating talk right now.
Hello, I'm Takeaki Sugimura, VP of Engineering at Cybo in Japan. I'm also a member of International Society for Advancement of Cytometry, ISAC, and I have been an ISAC innovator since last year and a member of the Cyto Innovation Committee. I'm enjoying these activities very well. I'd like to talk about how to build a system to introduce imaging innovations into cytometry. Let me briefly introduce my background and our challenges. My background is originally engineering, such as image processing and digital system design. Cybo is a startup company, and we are challenging to create innovative devices. We focus on digital microscopy for medical applications, such as digital pathology and cancer detection. We currently work on the development of a high-end and affordable digital microscope and cloud-based back-end software architecture. The goal is to support and automate inspections and speed them up with AI. In addition, we aim to use AI to separate cells from images for further analysis. This technology is called Intelligent Image Activated Cell Sorting, and it is the technology on which our company was founded. What is the key image for innovation that combine imaging with cytometry? My image is electric board. I know there are various technologies such as microfluidic devices and single-cell analysis. From my point of view, I would like to describe how to build a system for imaging. The reason my image is an electric board is because new edge devices bring new opportunities for real-time image processing implementations. What will be required for the prototyping of imaging system and the subsequent transition to commercialization? This is a schematic of the Intelligent Image Activated Cell Sorter system that we developed mainly in a lab at the University of Tokyo. This is a laptop equipment for proof of concept, and the image processing system consisted mainly of several high-end desktop PCs containing multi-core CPUs and GPUs, and several FPGA boards to realize hard real-time system. As the next step, to make prototype for commercialization, let me think about developing as a conventional closed industrial embedded system. What we need are, after deciding the specifications, consider the necessary components, sign NDAs with suppliers, and obtain the necessary information and software. In the most of cases, expensive evaluation boards and development environments need to be installed. We may need to obtain licenses for middleware too. It is also common to outsource the prototyping itself. Typically, these processes are closed, take a huge amount of time and money, and only limited organizations can do it. In contrast, many edge devices for imaging systems have been supplied in recent years, allowing small startups and even individuals to proceed with the development of their own imaging systems. Here are some edge computing devices, all of which have camera interfaces, multi-core CPUs with affordable memory, programmable accelerators such as hardware encoder, GPUs, or FPGA for image processing workloads, and also can be bought $200 or less. Cameras that can be connected to such boards can also be obtained for about $50. And with each new product released each year, the performance per cost has improved dramatically every year. In terms of software, all of the above boards run Linux-based open source operating systems, and development environments for image processing accelerators are usually provided free. With these edge devices, the development of imaging systems have certainly become much more accessible in the past few years. We are also using some of these for our development too. I believe that these edge devices will become increasingly important in realizing new instruments that combine cytometry and imaging systems. Thank you very much for your attention. Although I could not join in person today, I would be happy to interact with you. Thank you.
Really fantastic talk. Okay, so if you have any question, we have provided some opportunities to ask those, and then we can pass through the innovators. Then you can be in touch with them. Don't hesitate to ask your question in the box that have been provided for you. The next innovator is Dr. Hamber Hu. He is an assistant professor at Nanyang Technological University in Singapore. His research focus is on developing novel microfluidic point-of-care testing and organ-on-a-chip technologies for translational, diabetes, and cardiovascular diseases research. The article he is going to explain now was published in Lab on a Chip, so I encourage you to have a look at the great article he published, where you can see how microfluidics can significantly improve and control the exact movement of cells and particles. So let's listen to the talk now.
Hello everyone, my name is Han Wei and I'm from the Nanyang Technological University in Singapore. If you look at the picture on the right, it is a box of oranges and apples, and my question was, how can you distinguish them without looking? Intuitively, you will be using your sense of touch, where you will use your hand to try to feel for the texture, as well as to squeeze the fruit a little bit. Similarly, if we look at biological cells, shown on this slide are different kinds of leukocyte subtype. If we don't do any staining or use flow or imaging cytometry, how can we distinguish them? Again, we can also apply the sense of touch, but the difficulty will be how can we do it at the microscale level? This is where we will be introducing our technique, and this is known as microfluidic impedance cytometry. In short, impedance cytometry is a single cell characterization tool which is based on the dielectrical properties of cells. If you look at the pictures on the left, we have a microfluidic chip, and then we have a microchannel where we'll be flowing single cells through an electrode. Whenever the cell passes through the electric field, it will disrupt the field that cause a corresponding change in your current or impedance. And based on the size of the cells, this can actually be related or be used for cell sizing, which allow us to determine different kinds of cell type within a population. For the past few years, our group has been exploiting this impedance cytometry to look at leukocyte activation, and we found that by measuring the electrical properties at different frequency, we are able to tell different properties of the cells, such as the cell size, the membrane properties, as well as the nuclear properties. And we have shown that this technique actually works to look at the profiling of leukocytes, neutrophils, as well as T cell activation. Recently, we have also used this method to look at single microcarrier and spheroids, which have applications in cellular manufacturing. You may ask, why do we want to look at things in a label-free manner? Well, another important technology in our lab is on the label-free cell sorting using spiral technology, and combined with a label-free cell sorting and label-free detection, we have recently developed this chip which allows us to do a inertial and impedance cytometry at the same time. Briefly, whole blood can be introduced into the chip, and what it's going to do is at the cell sorting section, we're going to isolate the neutrophils from the red blood cells based on the size difference. We're going to align the neutrophils before we're going to send them for electrical detection. So during the cell sorting, the cell detection is also happening simultaneously, and with this we can actually measure different kinds of electrical properties to plot the impedance profile. And so this really becomes a sample in, answer out kind of method. So within 5 minutes, we just need to inject the blood sample into the chip, and then we can get the impedance profile of the neutrophils in 5 minutes. The application of this is to use it for clinical testing. For example, we have demonstrated that the electrical profile of diabetic immune cells are actually quite different from healthy individuals, and this can be used as a very rapid electrical-based inflammatory profiling. Moving forward, what we envision for our technique is that if you go, instead of looking at the current blood test, whereby they only use the hematoanalyzer to give you cell numbers on your immune cell population to indicate inflammation, we envision that with this impedance-based inflammatory profiling using our method, this can actually give you more comprehensive status of the immune level as well as the inflammation level in an individual. And we envision this can be used as a rapid test, less than 15 minutes, for immune risk stratification. That's the end of my presentation, and thank you very much for your attention.
Amazing, really glad to see how microfluidics, especially cell sorting devices, are controlling the particle movement and separation in these new emerging cytometry devices. So the next innovators that we have is Dr. Shih-Ming Tsai. We are really glad that he's now live today. So after his talk, we have the chance to have a live question and answer here. So Dr. Tsai received his PhD from UC Merced Interdisciplinary Program combining material science and bioengineering. His goal is to apply the knowledge and the experience of his biomedical and material science background to the development of in vitro diagnostics devices. What I really enjoy from his biography, to be honest, is the text he wrote, which he believes the microfluidic-based diagnostic devices will dominate the future of medical diagnostic field, which is absolutely true. Currently, he is the project leader for the non-invasive cell-based prenatal test. Their mission is to provide an alternative prenatal test for the pregnant women with a more precise testing result than cell-free DNA-based NIPT and a safer sampling method than amniocentesis. So let's listen to his great talk.
Hi, I'm Ming, the next generation cell-based prenatal test project leader in Phoenix Biotech. We are excited to announce that our tremendous progress in the development of these products. We know the major commercial prenatal test contains invasive method like detecting a gene disease from infant cell through an array-based DNA microchip, and the non-invasive way to get the mother's blood to analyze the possible chromosome issue from cell-free DNA for the infant. In phonics, we want to provide an alternative prenatal test option for pregnant women to select with a more precise testing result than cell-free DNA-based NIPT, the more safety sampling method than immunosynthesis. Currently, NIPT can detect 10 to 100 gene defect, and the array CGH can provide the diagnostic result on all the major gene diseases. Our preliminary data shows that we are possible to get the whole gene from our enriched cell sample. Our bioelectronic microfluidic chip can enrich infant trophoblast cell and provide enough cell for whole gene screening on gene diseases. Most importantly, we want to offer the test in the first trimester, as early as around 7 weeks to 12 weeks of pregnancy. This figure illustrates our device design. What does the chip look like now? The biospeed was first injected into the microfluidic chip after series wash step to eliminate non-surface binding. We apply electric cycling to change the material and the cell interface to release the cell by a high flow rate. There are several advantages for the bioelectron microfluidic chip on the next generation prenatal test and in our medical detection application. Our goal in here is first to use our bioelectronic microfluidic device to get the cell and use those cells to analyze the gene disease or gene sequence compared to the generation 1 array CGH result and the generation 2, the NIPT non-invasive method on spacing on the trisomy defect. And furthermore, we want to use more like a high-risk pregnancy woman sample to see if we can get more complicated diseases such like more than 300 CMV disease or single mutant for older gestation. The advantage of our device is first, we can eliminate the non-surface binding cell by high flow rate because our flow rate is quite higher than most of other microfluidic devices. And with this microfluidic device flow rate and the chip design, we can reduce the clock issue with our high tolerance device channel design. And because of the infant cell is pretty low in the blood or in all kind of sample, our strategy can obtain enough cell with a big base of the sample by the chromosome sample. Short period of time operating is another advantage of our device because we use higher flow rate and the electroplating cycling can quite fast to release and capture all the cell. Then with this high loading flow, possible much like the can isolate cell in one chip to get all the cell out to do the further analysis. And thank you for my collaborator, Professor Xiao, Professor Chen, and Senting, and also the ISIC provide me a chance to show our progress in this conference. Thank you for your listening.
So amazing. So now we have Dr. Tsai here. So if you have any questions, you can ask him right now directly so that we have the advantages of having him live. So Dr. Tsai, do you want to say something about your development, please?
Hi. Oh, excuse me. Actually, we are trying to find a collaborator for the IRB research for our device, because this is quite hard to get enough pregnant women to join this kind of study. So I'm here to reach out if there's any chance we can cooperate, or if you're interested of our device, can you just contact me and we can try to organize some cooperator to try and test our device and hope we can really get this product on the market in the few years. Yeah, so welcome any question. Because I cannot show too much detail on the device, we are in processing for the patent and the paper manuscript submitting. So just only can show a few figure here. Thanks.
Amazing. So let me please ask one question from the device that you have shown. I know that you said it's in the stage of patenting and filing, but I don't think it's a really special question. My question is that, is your device a handheld device, or you should use syringe pumps or those devices to run the fluid inside the channels?
For now, we use like a multi-channel syringe pump for the whole operating, so we can set up a program and we just loading our sample in different sample collector tube, and exact the program then will automatically finish all the program, all the processing. So it's kind of easy way for now. But our goal is maybe we can combining all the, right now we separate the electro chemical analyzer part and the pump part for the two different machines. Our goal is to combine these two function into one small machine to easy do the job. Yeah.
I have one question. Sorry.
Yeah.
How many trophoblastic cells typically you isolate from one tube of blood?
From the literature, they say we use COVID sample. They say the cell you can get is around 700 to 2,000 trophoblast cell, but partially of them maybe is combining mother and the kids cell together. So that will need to further like use like an IPT or NGS method to separate two different group and to see if there's any gene defect inside. Yeah.
Okay, thank you.
So amazing, Dr. Tisai. So I'm sure if there is any other questions, they can ask in the chat box and you can answer them through that platform or in the QA question box that we have provided for further collaboration and contribution in the field. So the last innovator here is Dr. Stewart Hanna. His interests lie in the development of diagnostic tests for a range of important conditions such as antimicrobial resistance, cancers, biomarkers, and infectious diseases. He develops novel low-cost electrode systems suitable for the use at the point of care. These systems typically exploit electrochemical techniques for the rapid detection, including electrochemical impedance spectroscopy. So now let's listen to his fascinating talk.
Hi there, I'm Dr. Stewart Hanna from the Department of Biomedical Engineering at the University of Strathclyde in the United Kingdom. And we're tackling the major global threat to public health that is antimicrobial resistance, or AMR. And each year, AMR is responsible for 700,000 deaths across the globe. And that number is estimated to reach 10 million by 2050, unless radical interventions such as rapid testing technologies are introduced. The challenge that we face is the current gold standard technology to assess the optimum antibiotic for a patient takes at least 2 days, which is too slow for proper infection control and can have a severe impact on patient health, for example, sepsis. So at the University of Strathclyde, in collaboration with spin-out company Microplate DX, we're developing the Microplate technology, a low-cost, mass-manufacturable, rapid in vitro diagnostic sensor test. where a patient delivers a standard sample, be it blood, urine, or sputum. It's then distributed across an array of gel-modified electrode sensors. And by modifying these electrodes with these special gel deposits containing different nutrients and a panel of different antibiotics, and by monitoring changes in electrochemical properties such as impedance over time to develop growth profiles, we can very quickly with this technology ascertain whether A, an antibiotic is required, and B, if it is, select the optimum antibiotic for treatment in under 1 hour. Our proof of concept work started by looking at Staphylococcus aureus and comparing that to the drug-resistant strain MRSA. This was published in 2019 in Biosensors and Bioelectronics, and you can see in the curves at the minimum inhibitory concentration, amoxicillin around 8 micrograms per mil, it inhibits the growth of the drug-susceptible strain Staph aureus, but MRSA, the drug-resistant strain, continues to grow at this antibiotic concentration. And it's only when you put a much higher antibiotic concentration, 50 micrograms per mil, into the gel, does it start to inhibit its growth. And clear differences were seen between these two strains in under 45 minutes. We then moved on to looking at gram-negative E. coli detection. We slightly modified the setup to enable measurement over a far longer measurement window. And in this case, we'll be using the antibiotic streptomycin. And you can see here the traces where there's red, there's no antibiotic contained within the gel, and the blue traces are an N of 3 showing different sensors set up with 4 micrograms per mil of streptomycin, again around the minimum inhibitory concentration. And we can see clear differences starting to appear within around 2 hours or so. And this was published in 2020 in MDPI Biosensors. So we took that proof of concept work and we've now started applying this to the first commercial application that we're looking to put in place and performing some clinical work around using microplate to detect urinary tract infections, or UTIs. These account for almost 14% of all antibiotic prescriptions in the UK NHS. Starkly, 1 in 3 women will get a UTI by the age of 24, and 1 in 4 sepsis cases can be linked back to an earlier UTI. So there's a real need to detect these early. So this work here was looking at 2 E. coli strains, one trimethoprim susceptible, denoted by the S on the figure, and one trimethoprim resistant, denoted by the R, spiked into real healthy volunteer urine. We performed a baseline, which was effectively a control that contained urine, healthy urine only, which is seen in red. So the only trace that matches the baseline and essentially doesn't grow is a susceptible E. coli strain in the presence of trimethoprim, as you would expect. All other traces, as you can see from the green, blue, and brown traces, are instances where the bacteria is able to grow on the surface. And we can see in under 30 minutes in this case, a clear difference between the susceptible strain with trimethoprim and the resistant strain of trimethoprim, performing antibiotic susceptibility testing in under 30 minutes. So in conclusion, we've developed a low-cost, rapid in vitro diagnostic test to be able to perform antibiotic susceptibility testing at the point of care and has broad appeal for a wide range of infections. The proof of concept work on MRSA showed a time to result of under 45 minutes. And we're now seeing clear differences between trimethoprim susceptible and resistant E. coli urinary tract infection strains in under 30 minutes. Future work will involve finalising the current clinical study we're performing with patient samples and ramping up the commercialisation of this technology with the spin-out company Microplate DX Limited. Thank you very much for listening today. I just wish to thank a number of our partners and funders, including Microplate DX, Scottish Enterprise, the Royal Society of Edinburgh, and Nesta Challenges. Thank you very much.
So that's really amazing. Glad to see so many number of clinical experiments, and we are really hoping to hear more about their journey toward the commercialization of their product. So now the section of Cytometry Innovator has been finalized. I'll pass it with Rob to continue the workshop with some nice discussion panel that we have right now. So Rob?
Yeah, thanks, Sajjad. So this is sort of the open discussion part. I know we're running late and we've got a couple of minutes, but I thought what we might do is I'm going to stop my share here. And we're going to invite some of the speakers that were able to join us today, Arnold, Majid, Stephen, and David, to have a little bit of a roundtable discussion here, and to see, just to try to get our heads around the innovation space and what that means in cytometry. So if you have some questions, please just put your hand up or unmute yourself and ask a question. We might just condense this into 10 minutes so we don't roll too far over. So I was going to open with a question for Majid, but he seems to have stepped away. So
I'm around. I'm around.
Oh, you are. I missed you. Yeah. So Majid, you've been in the space of. There we are. Look at that. Very flash. Majid, you've been in the space of the microfluidics area for a long time. So I just wanted to sort of get some of your thoughts about, what it looked like in the early days and how the integration with cytometry has sort of improved over the years.
Okay. Again, some microfluidics to me has seen its boom literally in the past, let's say 6 to 7 years. Probably 10, 15 years ago, for majority of scientists like us around the world, was a kind of toy development. Nobody was taking them serious as an actual device that can do functional assay and testings. But since bigger companies like Miltony Biotechs, like BD, and other companies started to utilize the benefit of microfluidics into their devices, particularly flow cytometry tools, and then you see the next generation of flow cytometry tools came out, we could see in a boom in both adaptation and both maturation of these devices. And then, of course, lots of pioneering works Gesude is doing in around image-based cytometry, which is technically is transforming or adding new modality in a way that we do, or stuff that one of the presenters present today around the deformability, which in fact there is currently 2 or 3 commercial products out there for disease diagnosis based on a cell deformability and cytometry. So this is certainly exciting time, and then with the fact that all these single cell technologies like 10x genomics and BD Rhapsody and all these droplet based stuff emerge, and they are finding their way into a spatial biology, we could see again new dimensions. It has been very, very rapid transformation, to be honest. I just don't understand why all of you are the background are white.
Because you're on the beach.
Is that the case?
I think the camera's not on. I think that's maybe the issue why they're not seen. So.
No, I think it's because, is it yours animated?
Oh yeah, mine is animated, and it shows all of you like with a white background. So it's the internet delay or something. So let me remove my background.
Yeah. Well, Majid does that. John, did you turn your camera on because you had a question?
Is that better now? So do you see me now actually or not?
We see you. We can see you.
Yeah, okay. So surprisingly for all of you, it shows a white background for me now. So you all look a ghost, all of you, to me now.
That's just because your version numbers for your Zoom is probably lower. That's why you cannot cope with.
Okay.
Yeah.
So Rob, I don't know how much. Upgrade. Yeah, I don't know. Okay, so I don't know how much I answer your questions, but again, playing with early devices probably 10 years ago, which was all PDMS and molds and things like that, with much more sophistication that you see now in a Fluidigm products, in, as I said, 10x genomics, in all these fancy tools that you guys are playing, which all of them have a component of the microfluidics, is so exciting. And of course, the challenges that everybody was elaborating today, these are immense opportunities that I can see we can tap into both in diagnostics and therapeutic side of the story. And microfluidic is definitely the future, and its integration with cytometry or cytometry-based microfluidics, that's the way to go. There is no other way around to me.
Yeah, no, I think it's an exciting time. So, is there any questions from the audience that we can pose?
I had one, Rob, and it was just how does everyone think that it is appropriate to balance complexity with usability and price? So that whole contrast, we want a lab on a chip ultimately, but how does one? And I think I have some views on the answers, but I'd be curious to get some feedback on that from the other team members.
That's such a great question. Oh yeah.
Again, it will go down to the context and usage, right? So if it's like a device that Stephen and the company Microgenesis is developing is a single-use device, it get the job done fast and make the life of embryologists easier, that's great. And value proposition for the price and the end user, it will be dictated how responsive is the market or how much you can stretch, right? It's just a matter of business rather than the size of the story. But when it comes to more sophisticated cartridges like the one that you use for the BD to load your beads and single cells and stuff like that, or the Fluidime cartridges, which cost you a few $1,000s, that's again another thing. So the ultimate aim is like sequencing stuff that Illumina is just pushing the boundary to bring the cost down and down every year. Beside the chemistry and biochemistry side of this story, the ultimate aim is to put these technologies in hands of more people. One frontier lies is definitely clinical scientists and scientists, but the bigger market is clinics and hospitals, where you could see utilization of these technologies by millions of the people around the world. That's, I would see that the major driver, which is going to be the cost going to go down, because your cells when you're going to go up. Again, to me, it's a context-based scenario.
Yeah, I think that's true. And I think in some ways, at least in the single cell genomic space, we've been somewhat desensitized to cost, but I think that's changing. And what I always say to the companies that, when we talk to them, we say, well, people have a finite budget, and that budget is getting smaller and smaller with the poorer funding, at least in the academic space. And so the question is, as a price point, do we price it so that we can do a little bit, or do we try to price it and so that we can do a lot? And I always say that the academics will always spend the money that they have, all right? But if they can get more out of it, then it's better for everyone. So I think the lower price point is good. And I think what is going to happen, at least in the single cell space, is that we're going to come back around into cheaper technologies. And that's certainly what we're doing with, clinical programs that we're running. We do a discovery angle with the single cell space, but then we try to break that down to the pertinent information and bring it back to a much simpler assay in the end.
Yes.
What does everybody else feel?
One question, one comment. I think, I guess one of the things is also, if you've got let's say when you get your products out to researchers to use, potentially, try and look at expiry dates, that kind of situations, because if you want someone to invest or you buy more, and therefore the demand is higher and use more, and therefore trying to drive costs low. But at the same time, if the expiry date is a very short expiry date, not sure if it's a new technology, someone's trying to uptake it, you have no idea how fast it gets uptaken, how much you want to invest, and things like that. And if, for example, I'll just give myself as an example. In our facility, we got sort of bitten a little bit once, where we invested a big sum of money in buying a lot of reagents, and the reagents comes and it's only a 3 to 6 months expiry, and within that 3 to 6 months, the uptake was slow, and with COVID coming in, at the end of the day, a lot of the reagents get to a point where it's expired, and if it's tagged, especially on the product, a researcher might come and look at it and say, hey, why are you using potentially expired or going to expire products? And that's going to drive a lot of issues and things like that. So, this is something that you probably take into consideration as well.
Thanks, Eric. Arnold, is that your hand up as well?
Yeah. So I would just I think Eric's point is probably catch a little bit, and also Majid's point about the price. I think, and what I really like to follow up is the Majid mentioned this the big users from the clinical domain. That's also the biotechnology domain. I think that I cannot agree more, because I think I can see I used to work with the people in the BD in the States. So the BD is a company that really dominate the cytometry market, and to many people's surprise, they're most profitable, or the biggest market share from their products is actually syringes, tubes, and all these things supplied to this hematology units or the clinical people. And when you talk with them, I think there is very difficult for them to change from the traditional or conventional cytometry-based assays to new assays. This is because with the clinical guidelines and a standard, and also I think there's something we need to consider is about the reproducibility and non-biased this analysis. So this is something I think really fundamental in this field, that unfortunately it's different from our academia and the basic science domain, so that we are pushing for innovations and the new things. So on the other side, the clinical and industrial users, they don't want to change, because the cost for them to change is actually huge. So that cost is, to me, is the major cost to change. So I think. But I agree, like you've seen this new text coming and pushing the boundaries, like Illumina, for example, these things can happen, but that to me that's a top-down approach rather than a bottom-up approach. So I think that's just my observations. I think you need to work with the clinicians, the hematologist, for something. I think that fundamentally you need them endorsement. This change need to be done, and then you can see these things going forward. I mean, from the academia side, I think as Rob you just mentioned, the funding is getting shrink. Basically our spokesperson, the power is losing. So that's kind of the it's a little bit sad, but that's the case. So yeah, that's kind of my point.
So I believe, Arnold, what you said is correct, and the fact that us as an academic, we shouldn't be really worried about the cost down the road. If something get adapted, definitely it will draw the request for that products will justify either the cost or it will reduce it down. Example again, sequencing stuff that drastically drop, and same is happening for spatial biology, the cost of that. Or another example was innovation of, let's say, Milton Biotechs by introducing Protégé machine for CAR T cell preparation, right? John Roscoe is here. I guess John can comment on this. There was nothing like that, and it was desperately needed, right? You need an integrated closed loop platforms, microfluidic enabled, to get a bag of blood, isolate the T cells, enrich them, transfect them, purify them, expand them, make it ready for the customers, right? For the patient. And that's the major cost for the CAR T cell therapy. I mean, a lots of innovation, cytometry innovation is needed in that space. So again, what we can do is that we can redo our job by looking what is happening in frontier of, let's say, cancer research or hematology research or cardiovascular research, and how we can see that the need is there. The need for reducing the cost of, example, T cells, to bring it down to be affordable for everyone is there. The problem is those preparation stuff, sample preparation, washing, isolation, all those things, and how we can integrate this cool science we do to bring that cost down. That's what I'm saying. So either we need to look at the problem or the scenario that we want to address this way, or we just do the innovation and we hope that a big company like BD will acquire this. We will justify the price or integrate it into their existing workflow. And at the end of the day, they are the people who are in contact with major clinics and hospitals and all these trials, which eventually will help the translation of this type of technologies. But I ditto what you said in general.
But I think the approach you're proposing, I think, is the best. to look at the emerging areas and then use that as a leverage.
Great. Ali, you've had your hand up for a little while.
Hi, thank you so much for this impressive talks. I have a question. What is your recommendation for the developing nations, and what sort of opportunities exist for the developing nations, and how we can interact with the experts in this field?
Yeah, I mean, it's a good question, and it's one that we don't have an answer to, and that's why we have these kind of workshops. And so we welcome you to, to provide the feedback and to provide. I assume that you're joining us from a developing nation.
Yeah, I'm from Iran.
Yeah. So I think it's a good question, and I can put it to the panel. But I would say that it probably takes a little bit of thought and a little bit of groundwork from societies like the Australasian Cytometry Society, potentially from ISAC, potentially from interested groups, either part of those societies or outside of that, to come together and have these kind of discussions more often and see where we can go. I know that markets are emerging. I know that, Sajjad keeps telling me about how much power and potential there is in Iran, but in China and all over the world as well. So maybe we'll throw it out to the rest of the panel to see what they think is possible here.
So, I mean, one couple of suggestions based on my experience of interacting with such a scenario as Rob. For example, one of our Professor Tesai requested clinical trials, right? If you could find a partner in Iran, people who are working in prenatal screening, opening an IRB and establishing a clinical trial is much, much easier and less headache than what we do in Australia, right? In terms of paperwork and time to completion. And it can be operated at relatively much lower cost, given the incentives that is in place to give to the patients and data collection. This, for example, for one of our recent COVID works, we did that in one of those hospitals, and we collected far more COVID samples compared to what we do in Australia, right? Just one opportunity. Other thing is that from the cytometry perspective, we can think of having potential international scholarships down the road or top-ups for such students who are coming from these developing nations to do research around cytometry and to essentially help to expand the level of the research that here we do, and probably bring more fresh blood from those parts of the world, right? Fresh brains. That's the second suggestion. And the third thing is, again, this what I can say is that perspective of the cost. This is what Stephen elaborated. We are thinking that for the sales of our cytometry or microfluidic products, depending on the nations that we sell, the price is going to be hugely different, right? The cost that we're going to charge, hopefully, for these products is Australia. It's going to be very different in India and in Iran. Although it's the same products for the same purpose, but given the fact that we are considering that affordability by the region and by the nation. These are probably small things as a group we can think of, but as you said, that would be great. We have a kind of brainstorming session to see how we can leverage on these emerging opportunities down there.
Great, thanks, Majid. Are there any other questions? I know we're well over time now, so. No further questions. All right. Given that we are 15 minutes or over 15 minutes past, what we might do is we might actually wrap up here. I did say that I would ask some questions at the end, but what I will do is I'll package these up and I will put them out to all of the registered delegates. And I would like to take the opportunity to thank all of the speakers, whether they were here in person or were provided their talks pre-recorded. Of course, David and Sajjad for helping to moderate, and everyone for coming. And I would just reiterate that this, I hope, is the start of a longer term dialogue. We have some really interesting things that are happening, some really interesting regions for collaboration, some projects that we're working on that we would love to bring industry together, and we'd love to bring the developing nations together to really push forward cytometry and to do things that we just can't do independently, and to really get that concept of integration and innovation back into cytometry. So thanks everyone, and enjoy the rest of the conference.